Hello, I'm Kaden from Wolfpack, and today I'll be going over our movement algorithm that we developed this year. Alright, so jumping straight into it, I've already made a video about the autonomous control. This is strictly about movement and somewhat teleop enhancements. So the first thing that we use, as I'm sure many of you already know, is we use a Magnum Drivetrain and then we use two-wheel odometry. So going right into odometry, pretty straightforward, two pods perpendicular to one another. What we do, which is interesting that I haven't seen a lot of teams do, is we use a combination of both line-based and arc-based odometry. The reason for this is that at the beginning of the season, we put the IMU on a servo and we flipped it back and forth a bunch of times, and then we realized there was a certain digit, I believe, around the thousandths, where the IMU is simply no longer accurate, but has precision to claim that it is to a much higher degree than that. So effectively what we do is if this change in heading is less than what we've deemed the IMU to be accurate to, we just use line-based odometry. And when that's not the case, we use arc-based odometry. And for us, this has given us accuracy both while moving fast and while moving slowly. We find arc-based odometry to be more accurate while moving quickly and line-based odometry to be more accurate while moving slowly. Although I do believe that there is a better way to do this that incorporates a third wheel, but we did not tackle that this season. And the reason I say that is because if the robot turns back and forth too many times, then it'll eventually start to lose position. I'd say if it turns about 6 times, it could lose as much as 3 inches. Alright, now getting into the Magnum Drivetrain, and one of the first things that I think could be of help to a lot of teams. So you can assume that the Magnum drive base looks like this, and these vectors essentially demonstrate the power vector of the Magnum. And you'll see that since the rollers are faced at 45 degrees, I've angled these power vectors at 45 degrees. But in reality, they're more shaped like this, and this is due to the internal resistance and friction, along with other things to do with the Magnums that give them a favored direction. So how we found what these vectors were specifically is we drove full power forward and then full power sideways, and then we compared those two velocities to give us this vector. From there, what we do if we want to drive in a direction is we first draw the vector that we want to drive in, and we find the angle between that vector and the positive x-axis. Then if we rotate the entire plane of vectors so that our drive direction is pointing along the positive x-axis, then essentially all we have to do is then cancel out the vertical components of these vectors, and we know we'll drive perfectly in that direction. So how we do that is we simply find the magnitudes of these vertical components and then scale down the larger ones. And essentially how we do that is by proportionally scaling down the power of these motors so that the vertical components cancel out and then the drive base drives directly to the right. And so this basically means that the drive base will actually behave how you expect. When you tell it to drive in a direction, it'll actually go in that direction. The other thing that we use instead of having both a vertical and horizontal PID is along with, so one way I think teams often use to hold a position is they have a PID for their Y coordinate and a PID for their X coordinate, and that's because the drive base behaves differently vertically and horizontally. But we also incorporate other PID and horizontal powers into our movement algorithm, as I'll get into later. And so what we need is we need one PID that can control the drive base no matter its orientation. And the way we overcome these discrepancies between driving forward and sideways is once we've rotated the plane of vectors, as you see here, we then, as I'll get into later, we have some perpendicular powers that act perpendicularly towards the direction of movement. So what we do is we add up all these vertical components of these vectors, and then we compare them to the original in the most favored direction. And that essentially gives us a scalar that, in this case, is demonstrated as this yellow vector, that if that power was then scaled up by this vector, would yield the original favored drive direction. And then what that means is we can tune a PID to the favored drive direction, and then the drive base is able to handle it. It's able to calculate what that power should be given its current orientation. And I think this could be helpful to a lot of teams as well. So now jumping straight into the movement, we use Bezier curves to localize, but first, why Bezier curves and why use this movement algorithm at all? So a simple demonstration, this year in this game, this was approximately the size of our robot relative to the poles. And let's say for this example, we're starting here and we don't want to drive to this point, which was important to us this season, as in order to navigate more safely, we wanted to be able to navigate between the poles during autonomous and not simply go straight up and down the line. So the most obvious way to travel between these 2 points is to follow a curve roughly as such. And then I'll explain the difference between our movement algorithm and others. So if you take Roadrunner, Pure Pursuit, and then our movement, this is the main difference. You give them all this path, and first let's start with Roadrunner. If you give Roadrunner this path, it'll perfectly follow the path, but it really was made for encoders and wasn't made for odometry. So if you give it any error, it likely won't go to its final position, but if you get lucky, it might. But first of all, this is bad because it's simply not dynamic, and it means the robot would have crashed into the pole here and creating all sorts of problems. Pure Pursuit, on the other hand, isn't actually a spline following algorithm. It approximates one by you pass it in lines and you tell it the size of a circle that you want it to follow, and then what it'll do is it'll find the intersection between the circle and the line paths you've drawn, and that essentially smooths your path. But the issue you can see really quickly is if your robot's here, that's fine, but once your robot's here and your drive direction's that way, you're going to hit this pole. And the only way to really avoid that using Pure Pursuit is to create a path that kind of goes out and then back in, but that once again kind of defeats the point of pathing. So ours is the happy medium of both, in which you give it a path, specifically it follows a path that's able to follow any continuous path defined parametrically, and then it follows the path, but if given an error, depending on the state, it'll either target the end position or it'll correct back onto the path and continue to follow the path, which we found super necessary for this game. Now jumping straight into Bezier curves and how they're defined. This isn't super relevant, but it may interest some of you. So I'm going to go through this part fairly quickly. Bezier curves, all lines in the system I'm about to describe are defined parametrically from 0 to 1. So P0.0, P1.1, it's defined with T going 0 to 1, and those are the equations. This, if you combine these, simplifies to point slope form. Now, when defining a Bezier curve, it can be defined with any number of points, but the points have to be given in an order. So in this case, it goes bottom left, top right, bottom right. And what that means is how the path is calculated is it'll then draw lines between all consecutive points. And then let's say the T is 0.2 in this case. It'll go T of 0.2 across all of these lines. And then now you'll see we're given 3 points. So we do the same thing with these 3 points. And if you go over and over again, essentially you end up with a single point, and that single point belongs to the curve. And this is a helpful GIF to demonstrate how this system works, and it is quite satisfying. So moving on from that, kind of why Bezier curves, as I'll get into a bit more later. Firstly, they're really easy to derive as they're essentially polynomials, because they're all linearizations of points. And then another nice thing that you'll notice in this right here, where all the Bezier curves on this are quadratic, meaning they're defined with 3 points. But if you define a Bezier curve with 2 points, that's a line. So defining it with 3 points would be a quadratic. And each of these curves is defined with 3 points on this graph. So you'll see these green ones they both start and end at the top right and bottom left corner, and then are respectively defined by the bottom right and the top left corner. And something you'll notice that's nice about this for pathing in particular is that none of these curves go outside of this bounding box that's defined by these points. And if you look a bit more closely, what that also means is that the end of a Bezier curve is tangent to the last line that defines it. So that means it's really easy to connect Bezier curves and make them smooth into one another. You just have to make sure that the endpoint is first shared by consecutive Bezier curves, but then the last point of this starting Bezier curve and the first point of the next Bezier curve that's not the end point and start point are all collinear. And that means that the path will perfectly smooth into each other. So now for how we actually follow the path, like I said before, all our paths are defined parametrically. And what that means is we can find the velocity of the path by taking the derivative of x and y both by t. And that essentially gives us this red vector here. The magnitude is not of importance to us, as it pretty much means nothing in the circumstance, but the useful part is that it gives you the starting direction you should be driving in based on where you are along the path. And how we decide where we are along the path is we increment by a fixed value that we define, that we hard code. And then what the robot does is it increases the point on the path by that fixed value until the distance from that point and the robot is getting greater. And that essentially means the point before it was the point closest to the robot. And it also makes sure we never go backwards on the path. Moving on, like I said before, we have some perpendicular powers that we incorporate that I will get into specifically in a moment. But firstly, how we apply these powers is, so we have our original pathing power, and this entire movement system is designed with the intent of working at power 1, as we thought that's what's important. So we have to make sure that no numbers exceed 1 and that everything stays scaled properly below 1. So to start off, we have our initial driving direction, which I've just made vertical in this case for simplicity. But then we have corrective powers that are added perpendicularly to this. Now you'll notice the hypotenuse of this triangle would be much larger than 1, and that would quickly become a problem. So essentially what we do is we make the pathing power, what is passed in, the hypotenuse, and then we scale down the actual driving direction power, and this ensures that no motor power is over 1. And then right here, there is a calculated angle, which, as I described earlier, our robot is able to follow, our robot drive-based drives in a specific direction given an angle, essentially. So what we can do is just add this angle to the previous angle, and now we have our new drive direction that we should be driving in. And then how we calculate it very simply, the inverse sine of the corrective power over the pathing power. And then you'll notice right here that this corrective power took away from our pathing power. So what we've developed is a hierarchy of powers, as we also need to incorporate our heading power, which is simply for us just a heading PID, although I do believe there's a better way to do that. But the order goes corrective power, so we think it's first most important to be pushed back onto the path, then most important to be turning in a direction, because we want to be able to tell the movement algorithm to drive at power 1, but we also want it to be able to turn. So that means heading power has to come over pathing power. And then lastly, of course, our pathing power. So moving on to some of the specific horizontal powers we add. The first one is we have a PID that simply corrects based on our distance from the path, and it pushes us back towards the path. Pretty straightforward. But the next thing we also incorporate is centripetal force, and this allows us to adhere to really complex and sharp paths. So how we do that is by employing something called curvature. And curvature essentially is 1 over the radius of the circle that most closely approximates a certain point on a path. So this curvature for lines is 0 because there's no curvature to lines. But in terms of Bezier curves, as I explained before, which are essentially splines, this becomes very useful. So centripetal force, we calculate the radius, and then we use simple physics equations to get this force and then scale this force to a motor power, and that essentially becomes one of the corrective powers that I showed in the slide before. So this is a quick Desmos that we made just for demonstrating, but this is a Bezier curve right here. This one is cubic, and if I just start it right there, you'll see the circle is pretty good at approximating the path at the point that we're curious about. So going back to the slideshow, why curvature works. I derived my own way of defining or finding the radius of the circle that you probably won't find anywhere on the internet because it's horribly inefficient, but I think it's the easiest way to describe why curvature exists, or at least a way of understanding how it comes about. And then we use a more simplified form that we found on the internet, but are capable of proving ourselves if need be to the judges, which I think is really important. So jumping right into it, first derivative of a circle defined parametrically is always going to be the same no matter the size of the circle. It's pretty obvious in this diagram and also obvious with the algebra. The r simply cancels out in terms of the y derivative and the x derivative by theta. But then when finding the second derivative, what you need to know is you need to know how the first derivative is changing relative to x. But sadly in this case we don't have x, but we have the next best thing, which is the rate of change of x. So what we can do is we can find the rate of change of the first derivative by theta and divide that by the change in the rate of change of x by theta, and that will essentially give us our second derivative. And this is simply how the second derivative is defined parametrically. You'll quickly see now we have an imbalance in the number of r's, so the second derivative will contain an r, and that's also really obvious if you show a specific change in x. You'll notice that the change in the first derivative varies greatly based on the radius of the circle. So algebraically, this comes out to that, whatever. You could move things around so you can define r, and this is a really messy equation, but it shows that the first and second derivative at a point can give you the radius of the circle that it's defining. But that means if we're able to find the first and second derivative of the path that we're following, we can get the circle that most closely approximates that point. And it's pretty good. So this is a quick demonstration of before and after we incorporated this centripetal force into our movement. You'll notice on this one it whacks against the poles a bunch, unsurprisingly. We tried to move, in this example, we tried to move the path more in. That way it wouldn't bounce against the poles, but then what ended up happening is it would hit these center line junctions, which kind of defeats the point. So this is after we've incorporated it, and you'll notice it's much smoother with going around the poles and not hitting anything, as well as like tightly actually following the path so we can have an easier time creating the paths for our movement. Maybe they'll both run at the same time. Nope. All right. So teleop enhancement. I know many people were curious about this, and I hope this is of help, but it is a bit complicated. So this is the equation we use in autonomous because it's simply more efficient, as I outlined earlier. And when you're given a path in autonomous, this is pretty simple. You have x as a function of t, y as a function of t. So finding the first and second derivative, especially when your functions are basically polynomials, is rather simple. But something nice, or something that starts off shaky but ends up nice, is when you want to find the curvature of the path you're following in teleop, you're not given this nice path that's outlined as to where the robot's about to follow. All you're given is your x and y coordinate. So something interesting that we decided to do is if you take both and instead of deriving by t, derive by x instead, then what will happen is the first derivative of x is 1 and the second derivative of x will be 0. And although the derivatives of y are a bit long, it means the equation massively simplifies, and it's simply the hypotenuse of a triangle of 1 in the first derivative of y, then cubed divided by the second derivative of y. And what the first derivative of y in this case is simply the change in y divided by the change in x. And then the second derivative is just the previously logged first derivative minus the current derivative, and then divided by the change in x again. And so during teleop, we don't actually use the past 3 points specifically. We apply a ring buffer, and we found this eliminated a lot of noise and made this enhancement much more effective. So kind of moving on to like a visualization of this, I'll log the past 3 points, and like I said before, these aren't actually the last 3 points, but it's helpful. Moving on, we have the order of these points, so we can draw the lines between them in that consecutive order, and this gives us the first derivative. So this line right on the top will be the first derivative of y by x, and then because we have a change in the first derivative, we can get a kind of change in the second derivative, which isn't great, but it works pretty well. So you'll notice if we then find the curvature, it's not perfectly along all these 3 points, but it's pretty good. And so now when we get the joystick input, this is the direction the drivers want to drive in, but not actually the direction the drive base needs to apply power in to go in this direction. So how we take care of that, like I outlined before, is we first find the centripetal force vector necessary. Based off the curvature and our current velocity, we now get this perpendicular power to the applied direction of movement. And then we add these two vectors together, and then we scale it down once again so that we can be driving at power 1 effectively. So this blue arrow demonstrates the direction the drive base will be driving in to actually move in the direction of the white arrow. And this just makes it a lot more intuitive for our drivers, because you would expect a drive base to be driving in the direction it's moving. And this essentially takes into account all momentum that is on the drive base and leaves that out of the driver's control. So the final thing that we incorporated into our movement is velocity-based stopping. So essentially what this is you can use your current velocity and then the measured deceleration of the drive base to predict where the drive base would stop if all power was cut to it. And so that's demonstrated in this blue arrow here, and how we use this is we then compare it to the endpoint. So when the distance is greater between the predicted stopping point and the endpoint, we know if we cut all power to the drive base, we would overshoot the final point. So what we then do is we then transition into a mode where we essentially move the robot to where it's predicted to stop in the code, and then draw the vector between that position and the end position and use a PID to correct to this point. And essentially what this lets us do is glide into position rather than overshoot or jump back or need any sort of measurements. And this was really important for us, as we noticed a big flaw in our movement at Chesapeake is it wasn't able to dynamically handle different voltages of the battery, and this takes into account perfectly, along with deciding to stop not based on a threshold, but rather when velocity hit 0. Those were two really big changes that we made for Worlds. So firstly, this before video, which is actually the same video I showed before of it moving between the poles, you'll notice as it gets towards this end position right here, it bounces back and forth a couple times, and that's simply unideal. And then after we've applied this velocity-based stopping, you'll see that's no longer the case, and it glides into position. So that is everything that I've done in terms of movement and localization this year. My goal with this video was to share the ideas that I had come up with, and hopefully give people room to expand off of it, because I feel like there is a lot more room for this movement to grow. One specific example that I'll just demonstrate that I wish I did this season, but simply ran out of time. With this idea of using a power or a PID to then correct towards the final position isn't perfectly ideal, because that means at a certain point it stops following the path and rather targets the endpoint. And I think there's some way to incorporate the perpendicular powers while also taking into account how far away the robot is predicted to stop, to then more accurately follow the path and stop quickly. But besides that, that's everything I've come up with this season, and I hope to see more ideas to come in the years following to add on to this way of moving. So that's it for me, and I'll see you guys next time.